And I'm back. So everything that scientists thought that they knew about the ocean floors turned out to be wrong. They said it was flat and it was boring. Oldest rocks would be found there. Turns out all that is wrong. But we didn't know that until we had this new technology called echo sounders, also referred to as sonar. It was developed during World War II, and just like a lot of things get developed for a specific reason, usually it has some military reason, some defense reason. It turns out that there are other uses for these things that can be quite helpful, especially in the scientific realm. So the echo sounder allowed the seafloor to be mapped in detail, and that detail caused a revolution in the field of earth science. So the maps revealed that there are mid-ocean ridges. Longest mountain range in the world, turns out it's on the bottom of the ocean floor at these mid-ocean ridges. It's a continuous mountain range that runs through all the world's oceans. There were deep ocean trenches, there were seamount chains, and there were fracture zones on the bottom of the ocean floor. So in 1958, one of the map makers that was tasked with bringing the profiles mapped by ships at sea to life, when she did her analysis and started drawing out what the bottom of the ocean floor looked like, she found this narrow valley running down the middle of the mid-ocean ridge. So this was a very profound discovery, because if she was correct that this strange little valley was there, then this might prove that continental drift did happen after all. So it took a while before she was able to publish her information. She had to redo her work time and time again, because people they knew what impact this would have if they published these maps and the maps had that fracture running down the middle of the mid-ocean ridges. So she had to redo her work a lot. But at last, every time she did it, it turned out that hey, the crack was there. So at last her bosses agreed that she was right. And this woman was Marie Tharp, of the Marie Tharp that I put the link to the song on YouTube, Girl Talk. So it's like crazy girl talk when she was saying that she found this fracture down the middle of the mid-ocean ridges. So Marie and her boss, they began to reveal their findings at different colloquiums. And a colloquium is kind of like a college hour event. And at one of them, at Princeton University, Harry Hess was in the audience. Harry Hess was an interesting guy. He was a geology professor at Princeton, but he had enlisted in World War II in the Navy, and he ended up being a captain of a ship called the USS Cape Johnson. It was an attack transport ship, but it was equipped with new technology, and that new technology was sonar. So he and his ship made many landings in the Pacific Ocean, like Iwo Jima and the Marianas, and the whole time that he was flying his way across the North Pacific, he had the sonar going, and he was coming up with these ocean floor profiles across the Pacific. So he only understood the significance of those profiles after Marie Tharp and, okay, her boss, Bruce Heason, but he was the one that kept saying, you got to redo this stuff, redo it, because this can't be there. This narrow valley can't be there. But it was. So he gets credit. In fact, his name comes first on all the maps that Marie published, which is an outrage. But nevertheless, these two had discovered this global rift along the mid-Atlantic ridge. Well, if that is there, then that's the key to the movement that Wegener envisioned. Well, sounds like a good idea, but prove it. When Harry Hess saw this, again, he had been in charge of a ship that had sonar on it, and he realized the significance of this ridge. He didn't know it at the time he was making the profiles, and he looked at the profiles, but when he saw that, he realized, hey, this is it. This is where he came up with his idea of seafloor spreading. And if seafloor spreading is taking place, it's at these mid-ocean ridges, these rift valleys and these mid-ocean ridges where that can take place. Well, it turns out that that sounds like a great idea, but again, prove it. Luckily, there were geologists that were involved in doing research in other areas like paleomagnetism and using isotopes to date the age of rocks. And the findings in these two areas provided the proof that Harry Hess needed for his hypothesis of seafloor spreading. So this is how sonar works. It's a sound wave that goes down to the bottom of the ocean and then gets reflected back. The echo comes back. So there's this instrument on board the ship that can times let me say that again. That times the echo of the sound wave. So if there's a deeper part on the ocean floor, let me get my pen out here, so my laser pointer out here. If there's a deeper spot on the ocean floor, then it takes that echo a longer time to make it back up to the ship. If there's a higher elevation on the bottom of the ocean floor, then the return time is shorter. So this is a constant kind of thing with the timing being calculated. And then when you look at it, you can come up with this profile of the bottom of the ocean floor. Today we have what's called side-looking sonar, and it's way more precise than what they had back in the day. So here's Marie, and there's her boss, Bruce, and he's pointing at the Mid-Atlantic Ridge. And here's Marie. Marie was a geologist and oceanographic cartographer. During World War II, there was a shortage of geologists, so the petroleum industry was feeling the brunt. So they decided to go to different colleges and universities around the country and ask the chairs of these departments to recruit more women into the geology departments. And Marie was one of them. But she had an advisor, and her advisor said, well, yeah, but you need to have something to fall back on when all the guys get home from the war. So I suggest that you pick something alongside geology that you can concentrate on. And she chose drafting, which turned out to be a brilliant choice for her because that's what she was called upon to do when she got a job at Columbia University, their earth science research arm. So she turned the world of geology upside down when she found what she found. So these are the types of maps that she came up with, and you can see how meticulous she was. These are just crazy accurate maps. So these mid-ocean ridges here, and you can see how it trends through all the world's oceans. And then if you look at a close-up here, this is what we're talking about. This rift valley down the middle. It's not just the Mid-Atlantic Ridge where we have the Rift Valley down the middle. It's in all of the mid-ocean ridges in all the world's oceans. So again, Harry, along with a few other people, but Harry gets the credit for it. He said that he thought that new seafloor forms at these mid-ocean ridges where there's this greater heat flow coming up. And then it spreads away from the ridges, and this is how oceans get larger, from this lava that's pouring out on the ocean floor and spreading out like on a conveyor belt. So again, grand idea, but hey, Harry, you got to prove it. This is his idea. Warm material rising from the mantle. These are just convection cells. Warm material rising from the mantle, so this new seafloor is generated. That seafloor gets a ride, I should say, moves away on this convection current, and then it sinks back down into the mantle. And that's how new rocks are added to the ocean floor. Again, just a convection cell. Now this takes a long time. This convection cell takes about 200 million years to make a complete cycle. So, of course, there's going to be a criticism for Harry Hess. You know, how does this happen? And if this is happening, then how come the ocean floors aren't getting, how come the Earth isn't getting larger if new ocean floor is being created all the time? And Harry had an answer for that, because as a young guy, he had worked on, he had worked in this area right here. That's the Puerto Rico Trench. So they were interested in the trench. They didn't know what it was there for. They didn't know what the function of the trench was for, but they knew that it was something interesting on the bottom of the ocean floor. So Harry's idea was that the Earth isn't getting larger because that seafloor ends up being dragged down. It gets older, it gets colder, it gets denser, and then it's dragged back down into these trenches where it gets recycled. So again, great idea, but prove it. So it turns out that there are scientists that are working in other areas of science. Two particular areas called paleomagnetism and isotopic dating. Isotopes are used to determine the age. Turns out they have something, a very unique characteristic called half-life. And we can use that to determine how old something is if those isotopes are present in the rocks. So the findings in those two areas provided the proof that Harry Hess needed for his hypothesis of seafloor spreading. So let me explain. Magnetometers were being used on ships at sea to study the magnetism on the ocean floors, and the readings that were recorded were baffling to most scientists. There were areas of normal polarity and reverse polarity, and mirror images of these reversed and normal polarity were observed on either side of the mid-ocean ridges, which seemed odd unless seafloor spreading was happening. Lava erupts at the mid-ocean ridge, and magnetic minerals in the lava orient themselves to magnetic north just like a compass needle would do. These reversals, where the crystals would orient to the south, were totally unexpected and revealed that Earth goes through magnetic reversals, but on no regular basis at all. So the lava moves out on either side like a conveyor belt. And sorry, folks. Okay, it's a madhouse around here, so let me try that again. So the lava moves out on either side like on a conveyor belt, and the clincher for proof was when the rocks on the ocean floor were dated, the youngest rocks were at the mid-ocean ridges, and they get progressively older, moving away. Proof that Harry Hess was correct. And nowhere on the ocean floor are rocks any older than 200 million years old. Think about that. The oldest rocks on continents are 4 billion years old. What is going on the floor of the oceans that rocks are so young? Again, Harry Hess was correct. The older rocks are dragged back into the mantle and melted at ocean trenches on a 200 million year cycle. So what you're, sorry, there we go. There are a diagram showing how you have these mirror images of normal polarity and reverse polarity, and their mirror image of each other on each side of the ridge. Reverse polarity are the tan colors, normal polarity are the colors here. And so again, it happens on no regular basis, but we have names for all of these different reversals. So what you're looking at here is a map showing the age of the ocean floor in different colored bands. Red colors are the youngest rocks, and they are all at mid-ocean ridges. The blue colors are the oldest. They are all located at either passive areas where there's no plate boundary or at trenches where the old rocks go to get recycled. Notice also that this is the mechanism by which continents' plates move. The Atlantic Ocean is spreading apart at about an inch a year. So the Atlantic is growing while the Pacific is spreading in places, but also getting subducted. These very dark areas right here are all trenches all around the Pacific Ocean basin. So they're getting subducted, and it turns out that the rate of recycling is greater than the rate of spreading. So the Pacific Ocean floor is going to disappear. The other thing I would point out here, look how much wider the red area is here than over here. This is spreading at about an inch a year. This is like Formula One race speed over here in the world of geology. This is about 4 inches a year, which is incredibly fast, but it's being subducted more quickly. So the Pacific Ocean basin is disappearing as the Atlantic Ocean basin is getting wider. This sets up a new Pangea, because if the Pacific Ocean is spreading, then these continents are going to come back together again at some point. So all this is going on, the globe is changing, oceans are disappearing, and continents are getting larger and smaller, and they're changing their location. This then is what plate tectonics is all about. Tectonic comes from the Greek word tektos, which means to build, but things also get destroyed or rebuilt into other things. So the Earth's lithosphere, oceanic and continental, are riding atop these convection cells, and they move and change in relation to each other. So it turns out that the theory of plate tectonics is a combining and reworking of the two old ideas of continental drift and seafloor spreading. Alfred Wegener can be forgiven for not knowing what that mechanism was. Nobody knew what the mechanism was because it was out of sight. It was under the ocean floor, and the ocean floor wasn't being looked at until years later after Alfred Wegener died. But the mechanism for why it happens is there. It's in seafloor spreading, and that's what makes continents move. So we'll pick up next time here with the 3 types of interactions. How do these plates move in relation to each other? They are divergent, they are convergent, and they are transform. So I will see you next time.